208 earthquakes came out of 1 square kilometre of California desert this week, and the network watching for the single thing that would tell us whether that matters consists of 3 boxes bolted to the ground, the newest of them installed in 2006. The volcano underneath is called Coso. It has not erupted in 40,000 years. At 1 minute before 1 on Sunday morning, it produced its largest earthquake of the year, 2.5 kilometres down, and by the end of that same day it had produced 116 more. Every instrument we have says this is hot water and not magma. So why does the honest version of that sentence keep getting shorter the closer you look at it? Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs, and drop a comment and tell me where you're watching from tonight. Now, let's get into it. Part 1. 1 minute before. 1 in the morning. At 55 seconds past 12:59 in the morning, Pacific time on Sunday the 23rd of August, 2026, the ground underneath a stretch of California desert that almost nobody lives on tore itself apart at a depth of 2.83 kilometres. The instruments that recorded it are scattered across Southern California, and they agreed on the essentials very quickly. The break happened about 10 kilometres east-northeast of a wide spot in the road called Coso Junction, on the eastern side of the Sierra Nevada, at the northern edge of the Mojave Desert. 40 seismic stations contributed to the solution. The azimuthal gap, which is a measure of how well the station surrounded the source, came in at 35 degrees, which is good. The location error was about 160 metres horizontally and under half a kilometre vertically. The event went into the catalogue as CI41533416, and after human analysts reviewed the automatic solution and recomputed it properly, its final moment magnitude settled at 3.96. Round that up and you get a 4, a magnitude 4 earthquake, at 1 in the morning, 2.5 kilometres down, inside the Coso volcanic field. That last part is the part that matters, because the Coso volcanic field is not a mountain, and most people who look at a map of California have never heard of it, and it has not erupted in roughly 40,000 years. Let me tell you what it actually is, because the name does it no favours. When you hear the word volcano, you picture a cone, a single peak with a crater at the top, snow on the shoulders, a plume if you are unlucky. Coso is nothing like that. Coso is a scatter. It covers about 400 square kilometres, roughly 150 square miles, and inside that area sit 38 separate rhyolite lava domes, 14 basaltic vents, cinder cones the colour of dried blood, rough black lava flows, hot springs, and ground that steams in the cold. The domes are the strange part. They look from the air like circular walled pits, and people who see satellite images of them for the first time regularly assume they are looking at impact craters. They are not. They are the opposite of a crater. They are piles. Lava so thick and so full of silica that it could not flow away from its own vent squeezed up, stacked on itself like toothpaste, and then sagged slightly in the middle as the inside cooled and gassed out. Frozen in place. 40,000 years of desert wind and nothing else has happened to them since. The United States Geological Survey counts roughly 40 separate eruptions at Coso in the last 250,000 years. The most recent one that anybody has managed to date built a basaltic cinder cone called Volcano Peak, and the lava flow that spread out from its base, and the potassium-argon daton that comes back at about 39,000 years, give or take a rather generous 33,000. Call it 40,000 and you are close enough. There is one more wrinkle that the survey is careful to include, and that almost every news story about Coso leaves out. The exact wording is that some geological landform relationships suggest that the youngest lava dome may have formed within the past 12,000 years, but this young activity has not been confirmed via dating methods. Read that carefully. It means somebody looked at how one of those domes sits on the landscape, how little erosion it has suffered, how sharply its edges still stand, and thought, that looks young. Not 40,000 years young, 12,000, possibly less. And then nobody has been able to prove it either way, because the rock has not given up a reliable date. So when I say this volcanic field has been quiet for 40,000 years, understand that the 40,000 is the number we can defend, and there is a smaller number sitting behind it that we cannot rule out. 80 seconds after that magnitude 4, the ground broke again. Magnitude 3.36, 2.55 kilometres down, in essentially the same spot. Then 77 minutes later, at 16 minutes and 58 seconds past 2 in the morning, a third one, moment magnitude 3.51 at 2.78 kilometres. Hold those three numbers together for a second, because they carry more weight than they look like they do. In the entire Coso volcanic field, across the whole of 2026 up to the 20th of August, nearly 8 months, the public earthquake catalogue contains exactly 2 events of magnitude 3 or above, 2 in 7.5 months, and then in 78 minutes, in the small hours of a Sunday morning, Coso produced 3. There is one more detail from that night worth putting on the table early, because it is the detail that generates the most noise online every single time it happens. The magnitude 4 was not published as a magnitude 4. It was first issued automatically as a 4.1. Then it was revised down to a 3.9. Then it was revised again upward to the value that rounds to 4.0. 3 published numbers for one earthquake inside a few hours, and the number went down and then came back up. I will come back to that in detail, because there is a clean explanation for it, and it is not the one people assume. But notice the shape of it now, because we have been here before. Just a few days ago we were looking at a South American earthquake, where 2 national agencies published 2 entirely different magnitudes and 2 entirely different depths for the same rupture, and neither of them was lying. Seismology publishes drafts. It always has. The public simply never used to see them. Now. The reason I opened with the depth rather than the magnitude. 2.83 kilometres is shallow. For a tectonic earthquake in California, extremely shallow. The ordinary background events a few dozen kilometres to the south, out near Ridgecrest, were happening in that same week at 7 and 8 kilometres, roughly 3 times deeper. Shallow earthquakes at a volcano are exactly the thing that makes volcanologists sit up, because magma that is going somewhere produces earthquakes that get shallower as it climbs, and underneath Coso there is, definitely and confirmed, magma. That is not speculation, and it is not a channel making something sound more dramatic than it is. The survey's own language is that geophysical and geochemical studies detect a zone of partially molten rock underlying the centre of the Coso volcanic field. The California Volcano Observatory lists Coso as one of only 7 volcanic areas in the state with confirmed partially molten rock beneath it. There is a body of liquid rock down there. Everybody agrees. So we have a volcanic field with confirmed magma under it, quiet for 40,000 years, producing a magnitude 4 and 2 more 3s inside 78 minutes at a depth of under 3 kilometres. Here is the first piece of the answer, and I am giving it to you now rather than making you wait an hour for it, because it reframes everything that follows. Every published estimate of how deep that magma sits, and there are 5 separate studies using 4 different techniques spanning 46 years, puts the top of the reservoir deeper than the earthquakes. The shallowest credible number anybody has ever produced for the roof of Coso's magma system is about 5 kilometres. Most of the estimates are considerably deeper than that. The earthquakes are at 2.5 to 3. The swarm is not coming from the magma. The swarm is happening in the rock above it, in a layer the magma has not reached and on every measurement we have is not currently trying to reach. That should be the end of the story. A shallow tectonic swarm, unrelated to the melt underneath, alert level unchanged, nothing to see. And for most of this video that is going to look like the correct reading, because it probably is the correct reading. But there is a problem with it, and the problem is not in the data. The problem is in how thin the data is, because the way you prove an earthquake swarm is not magmatic is not by looking at the earthquakes at all. It is by looking at whether the ground is swelling. That is the test. That is the single measurement that separates hot water from rising rock. And the observatory says so in plain language in its own public explanation of how it makes these calls. And the network that measures whether the ground at Coso is swelling consists of 3 GPS receivers. The newest of them was installed in 2006. The alert level at Coso tonight is normal. The aviation colour code is green. Neither has moved. No information statement has been issued. And the most recent notice the observatory has ever published that mentions the Coso volcanic field by name is dated the 11th of July, 2019, 7 years ago. 208 earthquakes went into the catalogue in 5 days. Let me show you what that number actually looks like when you break it apart by day, because the shape of it is stranger than the size of it. Part 2. 208. Counting earthquakes sounds like the simplest thing in the world, and it is one of the easiest ways to mislead yourself, so let me be precise about what I did. I pulled the United States Geological Survey's Advanced National Seismic System catalogue directly, drew a circle 35 kilometres in radius around the published centre of the Coso volcanic field at 36.03 degrees north, 117.82 degrees west, and asked it for every earthquake of any magnitude between the 20th of August and the 24th. That is the same catalogue every agency and every news desk works from. No filtering, no cherry-picking, no minimum threshold. 208 earthquakes. On its own, that number means nothing. 208 is either enormous or trivial depending entirely on what Coso normally does, and Coso is a genuinely busy place. So the first thing to establish is the baseline, and I built it from the same catalogue, the same circle, the same query, for the first 19 days of August. 96 earthquakes in 19 days, about 5 per day. Now the comparison works. 5 a day for 19 days, and then 42 a day for 5. 8 times the rate the same patch of ground had been running at for the previous 3 weeks. That is the honest version of the number, and it is already substantial. But the daily breakdown is where it stops being a statistic and starts being a story, so let me give it to you day by day, in coordinated universal time, which is how the catalogue keeps its books. The 20th of August, 16 earthquakes. Slightly above the baseline, nothing you would notice. The 21st, 52. That is 10 times the ordinary daily count, and this is the day the local news picked up, reporting 7 felt tremors near Coso Junction, with the strongest at 10:30 in the morning. That event is in the catalogue as a magnitude 3.29, which the early coverage carried as a 3.4. Same earthquake, later number, and again, that is just the pipeline working. The 22nd, 9 earthquakes. 9. Down more than 80% from the day before, back within touching distance of the ordinary background rate. If you had been watching this in real time on the 22nd, you would have concluded it was over. A short, sharp swarm, a couple of days of shaking and then the usual quiet returning. That happens constantly at Coso. That is the boring outcome, and it is by far the most common one. The 23rd, 116. One day, 116 catalogued earthquakes, in a search radius that had been producing 5 a day 3 weeks earlier, 23 times the baseline, more than double the first pulse, and every single one of the swarm's 4 largest events, the magnitude 4, the 3.5, the 3.36 and one more, arrived inside that one day. The 24th, as I'm putting this together, stands at 15 so far, including a magnitude 2.73 at 51 minutes past midnight. Still running, still above baseline, 16, 52, 9, 116, 15. I want to sit on that sequence for a moment, because it does something that earthquake sequences are not supposed to do, and understanding why requires one piece of physics that I am going to use repeatedly for the rest of this video. When a large earthquake happens, it is followed by aftershocks, and aftershocks are not random. They follow a rule that a Japanese seismologist named Fusakichi Omori worked out in 1894, and it is one of the most reliable relationships in the entire field. The rate of aftershocks falls off roughly as one divided by the time elapsed since the main shock. Practically, that means the first hour is violent, the first day is busy, the first week is noticeable, and after that it tails away, and the curve only ever goes one direction, downward. It can be steeper or shallower depending on the rock, but it does not turn around. Coso's 5 days do not do that. They go up, collapse by 83%, and then go up again to more than twice the previous peak. That is not a decay curve with noise on it. That is 2 separate pulses with a trough between them. And there is a second thing wrong with reading this as an aftershock sequence, and it is the more fundamental one. In a main shock and aftershock sequence, the largest earthquake comes first. That is the definition. The main shock releases the stress. Everything after it is the surrounding rock adjusting. At Coso, the largest earthquake of the sequence arrived 72 hours after the sequence started. Look at how the magnitudes climbed. The first notable event on the 21st was a 1.93, then a 2.98, then a 3.29, then, 2 days later, a 3.96. The sequence did not decay from a peak. It built toward 1, over 3 days, with a full day of near silence in the middle. There is a name for a sequence that behaves like this. It is called a swarm, and the formal definition is almost embarrassingly simple. A swarm is a burst of earthquakes with no single dominant event, no main shock, no aftershocks, just many earthquakes in a small area over a short time, with the biggest one arriving whenever it happens to arrive. We looked at a sequence with exactly this signature a few days ago in southern Spain, where a series that had already decayed for 3 days came back and produced a second earthquake of an identical magnitude to the first, and the whole thing lost any claim to having a dominant event at all. Different continent, different rock, same structural fingerprint, and we saw it again on the creeping section of the San Andreas earlier this month, where the escalation ran backwards, and the sequence never produced the main shock it looked like it was building toward. Swarms matter here for one specific reason. Main shock sequences are driven by a single stress release. Swarms are usually driven by something that keeps applying stress, most often a fluid, moving through cracked rock, changing the pressure on faults that were already close to failing. That is the standard interpretation. It is well supported, and at a place like Coso, which sits on top of one of the largest geothermal reservoirs in North America, it is very nearly the default. Which brings me back to the number 208 and to a caveat I have to put on it before we go any further, because it is going to become the spine of this entire story. 208 is not the number of earthquakes that happened at Coso this week. It is the number the public network could see. The regional catalogue is built from stations that are, for the most part, some distance away. There is exactly one seismometer operated by the survey near the Coso volcanic field, and it was installed in 2001. The dense instrumentation, the downhole sensors, the surface array that sits directly over the field, belongs to the United States Navy, because most of Coso is inside the Naval Air Weapons Station at China Lake, and the Navy's Geothermal Program Office runs its own network to monitor the power operation. That network resolves earthquakes down to local magnitude minus 0.5, not 0, minus 0.5. Events so small they release less energy than a car door closing. And in one corner of the field alone, that network logs several hundred events every month. So the real count for these 5 days is certainly higher than 208, probably by a lot. And the honest way to say this is that we are looking at Coso through the wrong end of a telescope, counting only the events large enough to punch through to instruments that are not there. That is not a conspiracy. Nobody is hiding it. The survey publishes the fact that it has one seismometer there, on its own website, in plain text. But it does change what the number means, and it is going to change what the reassurance means later. Before that, though, I want to go back to the shape of those 5 days, the 52, the 9, the 116, because that trough on the 22nd is not a gap in the story. It might be the most informative 24 hours of the whole sequence. Part 3. The swarm that died and came back. 9 earthquakes. That is what the 22nd of August looks like in the catalogue, sitting between a day of 52 and a day of 116. A single quiet day, wedged between 2 pulses, and it is the piece of evidence that tells you what is actually driving this. Think about what has to be true for that shape to happen. Something applied stress to a patch of rock on the 21st, hard enough to break it 52 times. Then whatever it was stopped, or moved on, or ran out, and the rock went quiet for a day. Then it came back, harder, and broke the same rock 116 times in 24 hours, producing the largest earthquake the field had seen all year. A single stress release cannot do that. If a fault slips and dumps its accumulated strain, the surrounding rock adjusts and then it is finished. It does not rest for a day and then adjust twice as hard. Whatever is happening at Coso is being driven by something that comes and goes. There are only a few things in the shallow crust that behave that way, and the overwhelming favourite is water. I need to explain the mechanism properly, because everything else in this video hangs off it, and it is genuinely one of the more beautiful pieces of physics in the whole of geology. A fault is 2 slabs of rock pressed together. What holds them still is friction, and friction depends on how hard they are being squeezed. The weight of everything above pushes down and clamps them shut, and the harder they are clamped, the more sideways force it takes to make them slide. That clamping force is called the normal stress, and in ordinary rock at 3 kilometres depth it is enormous. You've got 3 kilometres of solid crust standing on the fault. Now fill the cracks with water and pressurize it. The water pushes outward in every direction, including upward, against the underside of everything above. It does not have to lift the rock, it only has to take some of the weight off, and every unit of pressure the water carries is a unit of clamping force the fault no longer feels. The friction holding the two sides together drops. The stress trying to slide them sideways has not changed at all. It was there the whole time, but suddenly it is enough. Geologists call this reduced effective normal stress. I think of it as the crust getting a hydraulic jack under it. The fault does not get pushed, it gets unstuck. That single mechanism explains why swarms exist, why they cluster in geothermal areas, why they cluster in volcanic areas, and why they come in pulses rather than decaying. A pressure front moving through a fracture network is not a one-time event. It travels, it hits a barrier, builds up behind it, breaks through, drains, and the pressure at the original spot falls back. 52, then 9, then 116 is exactly what a fluid pressure pulse working its way through cracked rock looks like from the surface. And Coso is not merely a place where this could be happening. Coso is one of the most thoroughly fluid-saturated pieces of crust in North America. The rock beneath the field is described in the technical literature as highly faulted, fractured, and hydrothermally altered Cretaceous and Jurassic plutonic basement, which is a formal way of saying that this is granite that has been shattered, cooked, and had chemically aggressive hot water running through its cracks for a very long time. The fluid down there sits between 200 and 328 degrees Celsius. The company operating on top of it quotes a steady source temperature of 600 degrees Fahrenheit, close to 3 times the boiling point of water at the surface. It stays liquid because of the pressure. There is an official version of this argument, and it comes from an unexpected place. The Pacific Northwest Seismic Network, whose job is watching cascade volcanoes, and which therefore spends its life distinguishing dangerous earthquakes from harmless ones, puts it about as plainly as an institution can. Minor changes in a system of cracks with hydrothermal solutions can cause multiple small volcano-tectonic earthquakes without indicating a period of volcanic unrest. That is a scientific network telling you, in advance, that hot water in cracked rock at a volcano makes earthquakes, and it does not mean the volcano is waking up. So the standard reading of the Coso swarm, the reading a professional would reach for first, is hot water finding a new path through broken granite 2.5 kilometres beneath a desert, unsticking small faults as it goes, in pulses. That reading has to survive contact with the rest of the data, and it does, comfortably. But I want to be precise about what it explains and what it does not, because that distinction is where the interesting part of this story lives. It explains the pulses. It explains the absence of a main shock. It explains why the magnitudes climb rather than decay. It explains why the events are shallow. It explains why Coso does this constantly, and why the field is described, without exaggeration, as one of the most seismically active regions in the United States, producing dozens of magnitude 1 and 2 events every week in ordinary times. What it does not explain on its own is why now. Something changed at the end of the 3rd week of August. 9 days earlier, the observatory's own weekly bulletin logged 13 earthquakes above magnitude 1 at Coso for an entire week, the largest a 2.8, utterly routine. Then, within days, 116 in a day and a magnitude 4. Fluid pressure does not spontaneously invent itself. Something either injected fluid, released fluid, or changed the stress state so that fluid already present found a new route. And there are exactly 3 candidates for what could have done that, which I will take in order: the tectonics of the region, the industrial operation drilled into the roof of the field, and magma. Before any of them, though, there is a test that cuts across all 3, and it is the one thing the catalogue can tell us that nobody else has bothered to look at. Because if fluid or melt is moving upward through this rock, the earthquakes have to move with it. And the coordinates of 208 earthquakes are sitting right there in the public record, waiting for somebody to actually plot them. Part 4. A box 1 kilometre wide. I went through the location of every significant earthquake in this swarm, and what came back is the single most striking thing in the entire dataset. It is also the thing that essentially nobody is going to report, because it requires opening a spreadsheet rather than reading a headline. Every one of them sits between 36.061 and 36.070 degrees north, and between 117.8375 and 117.8442 degrees west. Convert that out of decimal degrees and into something you can picture. That is a box about 1 kilometre long, north to south, and about 600 metres wide, east to west. 208 earthquakes, over 5 days, including a magnitude 4, are all coming out of a patch of ground you could walk across in 15 minutes. Smaller than a regional airport, smaller than a lot of shopping centre car parks. The depths are just as tight, and this is where it gets genuinely useful. Excluding 2 background events well to the south that are not part of this at all, every catalogued earthquake in the cluster falls between 2.26 and 3.51 kilometres deep. Just over a kilometre of vertical range total, and the clear majority of them are packed even tighter than that, between 2.5 and 2.8. So the source is a thin, flat lens of rock, roughly a kilometre across and a few hundred metres thick 2.5 kilometres down. That is not a fault system rupturing. That is a specific, small, confined volume of rock doing something. Now apply the test. If a fluid is rising, or if magma is climbing toward the surface, the earthquakes have to record that journey. The rock breaks at the leading edge of whatever is moving, and as that edge advances upward, the earthquakes advance upward with it. Plot depth against time and you get a trend, a ramp sloping toward the surface. This is not a subtle signal. It is the clearest, most unambiguous precursor in all of volcano monitoring, and it is the pattern that gets alert levels raised. There is no trend in this data. The very first significant event of the swarm, on the 21st, was at 2.63 kilometres. The largest event, 2 days later, was at 2.83, deeper. The last significant event before I put this together, on the morning of the 24th, was at 2.26, which is the shallowest of the lot. But it sits inside a scatter that has been bouncing between 2.3 and 3.5 the entire time with no direction to it. The deepest event in the cluster, a magnitude 2.34, happened at 3.51 kilometres in the middle of the most intense hour of the whole swarm, going the wrong way at exactly the moment a rising body would be going the right way. The earthquakes are not migrating. They are staying put. Whatever is pressurizing that lens of rock is doing it in place, repeatedly, without advancing, and there is a hard physical reason why they might be pinned at that depth, which is one of the more remarkable facts about this particular volcano, and which almost nobody outside the geothermal industry knows. Rock behaves in 2 completely different ways depending on how hot it is. Cold rock is brittle. Push it hard enough and it snaps, and snapping is what an earthquake is. Hot rock is ductile. Push it and it flows, slowly, like extremely stiff putty, and flowing rock does not produce earthquakes because there is no sudden break to radiate energy. The boundary between those 2 regimes is called the brittle ductile transition, and it sets the absolute floor for earthquakes in any given piece of crust. Below it, the rock simply cannot break in the way that makes a seismogram move. In ordinary continental crust in this part of the world, that boundary sits somewhere around 11 kilometres down. Beneath the Coso geothermal field, it has been mapped at 4 to 5 kilometres. The transition is bowed upward there, like a tent pole pushing up a canvas, because the rock is anomalously hot. Hot from the magma body underneath, hot from the geothermal circulation, hot enough that it starts flowing instead of cracking at less than half the usual depth. And you can see the consequence directly in the seismicity. The base of earthquake activity beneath the Coso field shallows to 4 or 5 kilometres, while the surrounding region keeps breaking far deeper. That single fact does an enormous amount of work in this story. It means the swarm cannot be deeper than it is, because there is nowhere deeper for it to be. Between about 5 kilometres and the top of the magma reservoir, the rock at Coso does not do earthquakes. It flows. Anything happening down there is silent by definition, which means the 208 events we can see are, unavoidably, only the events happening in the top few kilometres, and that the thing volcanologists would most want to hear, the sound of something moving in the deeper crust, is a sound this particular volcano is physically incapable of making. Hold on to that, because in a few minutes it is going to come back and cause a serious problem for a paper published in one of the most prestigious journals in science. For now, the geometry gives us a clean answer to the question the title asks. Something is moving at Coso. It is moving in a lens of rock a kilometre wide and a few hundred metres thick, 2.5 kilometres beneath the desert. It is not moving upward, and it is sitting well above where anybody thinks the magma is. The obvious next question is how far above? Not roughly, precisely. Because if the gap between the earthquakes and the melt turns out to be a few hundred metres, this is a very different video from the one where it turns out to be several kilometres, and the answer has been argued over by 5 separate research groups for the better part of half a century. The 2 events I set aside are worth a moment, because they show what the same region looks like when the cause is unambiguously tectonic. On the 21st and again on the 22nd, two small earthquakes were recorded 23 kilometres north of Ridgecrest, a magnitude 1.98 and a magnitude 1.78. They sat at 8.14 and 7.35 kilometres depth, roughly 3 times deeper than anything in the Coso cluster, and about 27 kilometres away to the south-southeast. That is the residual seismicity of the 2019 rupture zone, still ticking over 7 years later, in ordinary crust where the brittle ductile boundary sits where it is supposed to. Same week, same region, same catalogue, and the two populations do not overlap in depth at all. That separation is itself evidence that the Coso cluster is a distinct process rather than an extension of the Ridgecrest aftershock field. There is also a historical comparison that fits almost uncannily. In February of 1992, Coso produced a swarm that began on the 17th, peaked around the 20th, and was still declining on the 26th. More than 300 small high-frequency earthquakes, 8 of them above magnitude 3, the largest a magnitude 4 at 19 minutes past 3 in the morning on the 19th. The hypercenters formed a pattern about 3 kilometres long, elongated north-northwest, at 3 to 5 kilometres depth, and the focal mechanism for the largest event showed mainly strike-slip motion with a small normal component. There were no injuries and no damage. A tight elongated cluster, a few kilometres deep, hundreds of small high-frequency events, a largest event at magnitude 4 in the small hours of the morning. That was 34 years ago, and nothing came of it. Part 5. The magma is real. There is a body of liquid rock underneath the Coso volcanic field. I want to be completely clear about that before we go any further, because the rest of this video spends a lot of time explaining why the current swarm is probably harmless, and it would be easy to come away with the impression that Coso is a dead volcano. It is not a dead volcano. It is a volcano with molten rock beneath it, sitting quietly, which is a different thing entirely. The survey's language is flat and unhedged. Geophysical and geochemical studies detect a zone of partially molten rock underlying the center of the Coso volcanic field. The California Volcano Observatory, in its own public description of what it watches, lists 16 threat-ranked young volcanoes in the state, and then narrows to the ones where melt has actually been detected. 7 of them: Medicine Lake, Mount Shasta, the Lassen Volcanic Center, the Clear Lake Volcanic Field, the Long Valley Volcanic Region, Salton Buttes, and Coso. The question is not whether the magma exists. The question is how far down it starts, and that has been argued about since 1980. The first serious attempt came from Paul Riesenberg, William Ellsworth and Stephen Walter, working with distant earthquakes as their light source. The technique is elegant. Seismic waves from an earthquake on the far side of the planet arrive at a network of stations as an almost perfectly flat wavefront. If the rock beneath one station is slower than the rock beneath its neighbours, the wave arriving there shows up fractionally late. Collect enough of those tiny delays from enough distant sources, and you can reconstruct the shape of whatever is slowing them down. What they found beneath the Coso geothermal field was a body where seismic velocity dropped by as much as 8% between 10 and 17 kilometres depth. Partial melt slows seismic waves. That was the first hard evidence for a magma chamber at Coso, and it put it at 10 kilometres and deeper. 23 years later, Charles Wilson, Craig Jones and Hirsch Gilbert came at it with shear waves and found something shallower, a reservoir they placed at roughly 5 kilometres with a separate boundary near 15. Jeffrey Unruh and Egil Haukson, working with the three-dimensional velocity structure of the whole region, described something different again. A flat, sill-shaped body of magma about 20 kilometres long and 3 to 5 kilometres thick, sitting between 11 and 16 kilometres down. And in 2022, a group led by Wang published the most data-intensive version of the exercise yet, inverting nearly 138,000 direct wave arrivals, plus more than 8,500 waves reflected off the base of the crust. Their picture is a prominent low-velocity body between 5 and 20 kilometres, which they read as the rhyolite reservoir, with a deeper, more basaltic body below 20 kilometres, feeding it from the mantle and dipping away southward beneath Indian Wells Valley and the Garlock Fault. 5 studies, 4 techniques, depth estimates ranging from about 5 kilometres to more than 20. That spread looks like a mess, and for years it was treated as one. The modern reading is that everybody was right, because the plumbing is not a single chamber, it is a stack. There is basaltic melt arriving from the mantle at great depth, feeding a mid-crustal storage zone, feeding a shallower eruptible pocket of rhyolite near the top. Different techniques are sensitive to different parts of that stack, which is why they disagree, and the disagreement is informative rather than embarrassing. But look at what every one of those numbers has in common. The shallowest credible estimate anyone has ever published for the top of Coso's magma system is about 5 kilometres. The earthquakes this week are at 2.5 to 3. Even against the most aggressive, most alarming reading of the geophysics, there are 2 kilometres of solid rock between the swarm and the melt, and against the more typical estimates, there are 8 or more. And between the swarm and the magma sits that upward-bowed, brittle ductile boundary, a layer of rock too hot to crack, which is precisely the kind of barrier that pressure changes in a brittle fracture network do not propagate across. The swarm is in the wrong place to be magma, not marginally, not arguably. It is in a completely different part of the crust, separated from the melt by a zone that does not transmit the kind of stress changes we're talking about. There is one more piece of work here that deserves its own moment, because it is the single most unsettling thing anybody has ever measured at Coso, and it has nothing at all to do with this week. In 2000, Curtis Manley and Charles Bacon published a study in the Journal of Petrology that did something clever with the erupted rock itself. When magma sits in a reservoir before erupting, the minerals that crystallize out of it record the temperature and pressure they formed at. Pressure translates directly to depth. So if you collect rhyolite from domes of different ages and read the crystals, you can reconstruct where in the crust the magma was stored at each point in the field's history. They did that across the last 600,000 years at Coso. What they found is a trend, and the trend runs one direction. The oldest magma they examined, from roughly 600,000 years ago, formed at about 270 megapascals and 740 degrees Celsius. That works out to a storage depth of around 10 kilometres. The youngest, from the eruption roughly 40,000 years ago, formed at about 140 megapascals and 770 degrees, 5.5 kilometres, hotter and half as deep. Over 600,000 years, Coso's magma reservoir has been climbing, and their conclusion, in their own words, is the part that stays with you. As the reservoir has become closer to the surface, eruptions have become both more frequent and more voluminous. That is a real, peer-reviewed, 25-year-old finding, and it says that Coso has been slowly loading itself for the entire history we can read. It also says nothing whatsoever about this week, or this year, or this century. The clock it describes ticks in hundreds of thousands of years. Charles Bacon put an actual number on it in 1982, using the rate at which the crust here is being pulled apart. Rhyolite eruption within the next 60,000 years, give or take 35,000, and basalt within the next 55,000. He also found that for extension to actually produce a widespread eruption, rather than just squeezing magma into cracks, the rate of intrusion would have to exceed the rate of extension by a factor of 200. Those forecasts are not predictions in any useful human sense. They are a way of saying, this system is alive, it works on a schedule measured in tens of thousands of years, and nothing about a 5-day swarm changes where we sit on that schedule. So the magma is real, it is confirmed, it is rising on a geological timescale, and it is nowhere near this week's earthquakes. Which raises the obvious question. If all of that is settled, and the depths clearly rule out magma, why does anyone need to check anything at all? Why is there a monitoring network? What specifically would a volcano do differently, and how would anybody actually know? The observatory has published the answer, and it is more revealing than they probably intended. One more thing about that stack, because it explains why Coso exists at all, and why the melt is able to get as shallow as it does. Coso sits in what geologists call a right-releasing stepover. There are 2 strike-slip fault systems here, the Airport Lake and Little Lake fault zones running up from the south, and the Wild Horse Mesa and Owens Valley faults continuing to the north, and they do not join end to end. They are offset from one another, and the crust caught in the jog between them is being pulled apart as the 2 systems slide. Picture 2 escalators running side by side in the same direction, slightly out of line with each other, and imagine standing with 1 foot on each. That is the crust at Coso. It is not being compressed, and it is not simply being sheared. It is being stretched in a specific small area by the geometry of two faults that do not quite meet. Stretched crust thins, and thinning crust drops its pressure, and dropping pressure is one of the two ways you make rock melt without adding heat. The Airport Lake Fault Zone itself is catalogued as fault number 73 in the survey's quaternary fault database, 40 kilometres long, moving both normally and right laterally, with its most recent prehistoric rupture in the latest quaternary, within the last 15,000 years, at a slip rate somewhere between 0.2 and 1 millimetre a year. The Garlock Fault, which runs perpendicular to the San Andreas, is 60 kilometres to the south. That is the machine that built this volcanic field. Not a hotspot, not a subducting slab, but a gap between two sliding faults, pulling the crust apart slowly enough that magma has had 250,000 years to work its way upward through the space. Part 6. How you actually tell. In December of 2024, two scientists at the California Volcano Observatory sat down and wrote a public explanation of how they decide whether to raise an alarm. Jessica Ball, a research geologist, and Alicia Hotovec-Ellis, a volcanoseismologist. The piece is titled, more or less, What is Normal for a Volcano, and it is the closest thing that exists to a published decision procedure for exactly the situation Coso is in right now. It runs in 4 steps. The first is almost comically mundane, and it is the step that catches the most false alarms. Which stations does the signal appear on? Their wording. If a seismic signal only appears in one place, there is a good chance its source is very small and near the seismometer, or related to the equipment itself, a wobbly telemetry tower, a vibrating overpass. A great deal of what looks like volcanic unrest on a single trace turns out to be a loose bolt. The Coso swarm passes this trivially. 40 stations contributed to the magnitude 4 solution. It is real, it is in the ground, and it is where the catalogue says it is. The second step is depth, location, and the character of the signal, and this is where the actual seismology starts. There are 4 broadly different things a volcano can do to a seismogram, and telling them apart is most of the job. The first is a volcano-tectonic earthquake. Rock breaking, sharp onset, high frequency, short duration. On a screen it looks like a knife cut. These happen in cool, brittle rock, often some distance from the melt itself, and they can be triggered by stress from magma moving somewhere else entirely, or by nothing more exotic than pressurized water changing the friction on a fault. Every single event in the Coso swarm is this type. The second is a long-period earthquake, sometimes called low frequency. Hotovec-Ellis's description is the best I have read, broad and wobbly, as against sharp and distinct. These are not rock breaking. They are resonance, fluid or gas forced through a crack, making the crack ring like an organ pipe, and the frequency of the ringing tells you something about the size of the crack and what is inside it. Long-period events are shallow, and they are the ones that make volcanologists reach for the phone, because they mean fluid is actually moving rather than sitting still. The third is harmonic tremor, long-period events arriving so continuously that they merge into an unbroken signal that can run for minutes, hours, or days. Tremor is the sound of sustained movement. The fourth is surface events, rockfalls, avalanches, debris flows, glaciers, not relevant in a desert. The reason this taxonomy matters is Mount St. Helens, and it matters twice. In 1980, in the months before the eruption, the mountain produced both long-period earthquakes and volcanic tremor. And in 2004, when the crater began building a new dome, the seismic record shows a transition. The volcano-tectonic earthquakes gave way to long-period ones as magma pushed upward. That transition is the signature. It is what the rock does when melt stops sitting and starts moving. At Coso, there are no reported long-period events. There is no reported tremor. There is nothing but sharp, high-frequency, shallow, brittle breaking, the exact signal that hot water in cracked rock produces, and the exact signal the Pacific Northwest Network warns can occur in quantity without indicating volcanic unrest at all. Then comes the third step, and I want to give this one in full because it is the hinge of the entire story. Magma pushing into the subsurface has to displace the rocks around it and will cause deformation. The gases that come with it want to rise through the earth and eventually have to come out somewhere. If we don't see either of those things, the source may be too deep and probably not a concern, or it isn't magmatic and won't be moving upward. That is the test, not the earthquakes. The earthquakes are the thing that gets your attention, They are not the thing that answers the question. Magma is a physical object. To move upward, it has to shove several cubic kilometres of rock out of its way, and rock being shoved out of the way does not stay flat. The ground swells, sometimes by centimetres, sometimes by metres, sometimes over years and sometimes over hours, but it swells, and it is measurable long before anything reaches the surface. Alongside it, the gases dissolved in the melt, carbon dioxide first, because it comes out of solution deepest, then sulfur dioxide, force their way up through the fractures and appear at the surface as new fumaroles, or as a change in what the existing ones are exhaling. Deformation and gas. Those are the two independent physical non-negotiable consequences of magma moving. If they are absent, the observatory's own published position is that whatever is making the earthquakes either is not magmatic or is too deep to matter. The fourth and final step is patience. Are the signals getting shallower and stronger, or migrating through the subsurface? Or are they staying in one place? Are they tailing off at a rate that looks more like a tectonic earthquake, or coming in waves and bursts? We have already run that test on the catalogue ourselves. The Coso events are staying in one place, in a box a kilometre across, and they are coming in waves and bursts. Under the observatory's own framework, one of those observations argues against magma, and the other argues for fluid. Both point the same way, and there is a fifth thing in that article which is not one of the four steps, but which tells you a great deal about how this system is supposed to work. When something does start to look unusual, the observatory says, the first step is to talk with partners and issue an information statement about the activity. This is the first heads up we give before changing a volcano's alert level. It is deliberately a low bar. It is not an alert. It is not a warning. It is a note that says, we have noticed, here is what we think, we will keep you posted. No information statement has been issued for the Coso swarm. That absence can mean two entirely different things, and distinguishing between them is the whole point of the next part of this story. It can mean the observatory has looked at all of its data streams, seismicity, deformation, gas, and concluded correctly that this does not clear the bar. Or it can mean that the data streams which would clear the bar are not there to look at, because the test that decides everything is deformation. And I have been putting off telling you what Coso's deformation network actually consists of. It is worth knowing what the ladder above normal actually looks like, because the language is precise, and the two scales run in parallel. The volcano alert level, which describes ground hazards, has 4 rungs. Normal means the volcano is in its typical background non-eruptive state. Advisory means it is showing signs of elevated unrest above the known background level. Watch means heightened or escalating unrest, with increased potential of eruption on an uncertain time frame, or an eruption already underway that poses limited hazards. Warning means a hazardous eruption is imminent, underway, or suspected. Alongside it runs the aviation colour code, which describes the threat to aircraft from ash, and it has 4 rungs too: green, yellow, orange, red. When the alert level changes, the observatory issues a volcano activity notice. When the colour code changes, it issues a volcano observatory notice for aviation. Coso is at normal and green, and every other volcano the California Volcano Observatory watches: Mount Shasta, Medicine Lake, the Lassen Volcanic Center, the Clear Lake Volcanic Field, the Long Valley Volcanic Region, Uberheber Craters and Salton Buttes, is at normal and green as well. That is a system with a lot of room in it. There are 2 full rungs between where Coso sits tonight and the rung that means an eruption might be coming, and an information statement is not even the first of them. It sits below the ladder entirely, as a courtesy. Part 7. 3 GPS receivers. 3. There are 3 continuous GPS receivers making up the deformation monitoring network at the Coso volcanic field. The survey publishes this on its own website without embarrassment, because it is not a scandal. It is a budgeting decision. They were installed in the years 2000, 2005 and 2006. The newest instrument watching for ground swelling at a volcano with confirmed magma beneath it has been in the ground for 20 years. There is 1 seismometer operated by the survey near the field. It went in during 2001. There are no tilt meters. There are no strain meters. There is no gas monitoring listed at all. Now set that against the test we just established. The observatory's own published decision rule is that magma displaces rock and therefore causes deformation, and that gases rise and have to come out somewhere, and that if you do not see either of those things, then the source is not magmatic or is too deep to matter. That is a sound rule. It is the correct rule. And at Coso, the instrument that applies the first half of it is 3 receivers spread across 400 square kilometres, and the instrument that applies the second half does not exist. To be fair to everyone involved, that is not the whole picture, and the part that is missing is the part almost nobody mentions. Most of the Coso volcanic field lies inside the boundary of the Naval Air Weapons Station at China Lake. The Navy has an operating geothermal power plant sitting on top of the field, and a power plant needs to know what the rock underneath it is doing far more urgently than a federal science agency does. So the Navy's Geothermal Program Office runs its own seismic network, downhole sensors lowered into boreholes plus a surface array, and that network is genuinely excellent. It resolves earthquakes down to local magnitude minus 0.5, not 0, minus 0.5, which is an event releasing about as much energy as a heavy book hitting a floor. In the West Flank area alone, that network records several hundred seismic events every month, as routine background. So Coso is not unwatched. Coso is watched extremely closely by an organisation whose interest is electricity, and watched thinly by the organisation whose interest is eruptions. Those are not the same job, and they do not produce the same data. A network optimised to track a reservoir does not necessarily tell you whether the ground is inflating. For a sense of what the other end of the scale looks like, go 200 kilometres north to Long Valley Caldera. 46 GPS receivers, 9 tilt meters. A caldera instrumented so densely that the survey can resolve horizontal ground motion to about 3 millimeters and vertical motion to about 8. 46 against 3. Now, I want to be careful here, because there is a version of this observation that is simply wrong, and it circulates constantly. The version that says Coso is the volcano nobody is watching, the one that will catch us out, the real threat while everyone stares at Yellowstone. That framing is wrong, and the numbers say why. The survey's 2018 National Volcanic Threat Assessment scored 161 American volcanoes against 24 separate criteria, 15 hazard factors and 9 exposure factors. Hazard factors include the volcano type, the eruptive history, how explosive past eruptions were, how much time passes between them, what kinds of hazards they produced, and what the volcano is doing right now in terms of seismicity, ground deformation, and degassing. Exposure factors include the population within 30 kilometres, park and monument visitor numbers, prior fatalities, prior evacuations, aviation exposure, and the power and transport infrastructure in the way. 18 volcanoes came out as very high threat, 39 as high, 49 as moderate, 34 as low, 21 as very low. Long Valley ranks 18th of 161, with a score of 129. It is the very last volcano still inside the very high band. Coso ranks 72nd, with a score of 55. Moderate. Long Valley scores about 2 1/3 times what Coso scores, and the reasons are structural rather than arbitrary. Long Valley produced the Bishop Tuff eruption 760,000 years ago, which moved something on the order of 650 cubic kilometres of material. More than 100 cubic kilometres fell as ash. Roughly 200 more came out as pyroclastic flows that swept across 2,200 square kilometres, and about 350 cubic kilometres ponded inside the caldera and welded itself into rock nearly 200 metres thick. Coso, across 6 million years of activity, has erupted about 35 cubic kilometres total, and 30 of that came out in one Pliocene burst between 4 and 2.5 million years ago. Long Valley's most recent eruption was 16 to 17,000 years ago. Coso's was 40,000. Long Valley has the town of Mammoth Lake sitting on its edge and a major highway running through it. Coso has 370 people within 10 kilometres. Most of the field is a restricted military installation, and the nearest towns are Olancha and Pearsonville, neither of which most Californians could find on a map. The monitoring asymmetry is not neglect. It is proportion. Coso is instrumented roughly in line with what it can actually do, which is produce a modest eruption in a place where almost nobody lives. But, and this is the whole point, proportion is a statement about consequences, not about knowledge. The threat score tells you how much it would matter if Coso erupted. It does not tell you how well we would see it coming, and the honest answer to the second question, given 3 GPS receivers and no gas instruments, is less well than we would see it coming almost anywhere else on that list. There is a way to check this, at least partially, and it works in Coso's favour, because we do have a long deformation record for this field, even if the instrument count is thin and it runs the wrong way for anyone hoping for drama. In the year 2000, Yuri Fialko and Mark Simons published a study using satellite radar interferometry, a technique that compares radar images of the same ground taken from orbit at different times and measures how far the surface has moved between them, down to the centimetre. They looked at Coso across 1993 to 1999. What they found was subsidence, about 50 square kilometres of the Coso area sinking at a maximum rate of roughly 3.5 centimetres a year, representing a volume loss of around 1 million cubic metres annually. More recent radar work puts the maximum modern subsidence at up to 15 millimetres a year. The ground at Coso has been going down, not up, for as long as we have been able to measure it. That is precisely the opposite of what an inflating magma system looks like, and it is exactly what you would expect from a geothermal operation pulling heat and fluid out of the rock faster than nature puts it back. So the deformation evidence, thin as the network is, does not merely fail to show inflation. It shows a robust multi-decade trend in the opposite direction. That should be reassuring, and it is. But hold it up against the alert level for a moment. The alert level at Coso is normal, and the aviation colour code is green, and both have stayed there through a week in which the field produced 8 times its background earthquake rate, doubled its annual count of magnitude 3s in 5 days, and generated its largest event of the year at 1 in the morning. No information statement. Nothing. We ran into this exact shape yesterday, looking at a week in which 6 separate volcanoes on 4 landmasses changed state while the official numbers stayed flat, and the lesson there applies without modification here. An alert level is a statement about what an agency has decided to communicate, not a live readout of what a mountain is doing. Normal does not mean nothing is happening. Normal means nothing has happened that crosses a threshold somebody defined in advance, using instruments somebody funded in advance. And Coso has a precedent for exactly this. A week when the ground went genuinely wild, when the earthquake rate was not 8 times background but more than 100 times background, and when the answer, correctly, was still nothing to worry about. That was 7 years ago, and it started with the largest earthquake to hit California in 2 decades. Part 8. 34 hours. In July. On the 4th of July 2019, at 33 minutes and 49 seconds past 10 in the morning Pacific time, the Mojave Desert broke. The earthquake registered magnitude 6.4. Its epicenter sat at 35.705 degrees north, 117.504 degrees west, about 11 kilometers southwest of Searles Valley and 14 east-northeast of the town of Ridgecrest. It broke at 10.5 kilometers depth. In the catalogue it is event CI 384438183. It was, at that moment, the largest earthquake in Southern California in 20 years, and everybody who studies this for a living assumed it was the main event. The aftershock sequence began doing what aftershock sequences do. Thousands of small events, decaying steadily. Crews went out to map the surface rupture. The story looked finished. It was not finished. It was a foreshock. 121,564 seconds later, 33 hours and 46 minutes, essentially 34 hours, at 19 minutes and 53 seconds past 8 in the evening on the 5th of July, the desert broke again, and this time it broke properly. Magnitude 7.1, 35.769 degrees north, 117.599 degrees west, 8 kilometers deep, event CE 384575511. The geometry of what happened is one of the reasons this sequence became one of the most intensively studied earthquakes in American history. The 2 ruptures did not occur on the same fault, and they did not occur on faults that merge at depth, which is the ordinary arrangement. They occurred on 2 fault systems that cross each other at very nearly 90 degrees. The foreshock ran on what is now called the Salt Wells Valley Fault Zone, a mostly continuous left lateral structure trending northeast to southwest for about 18 kilometers, with maximum measured offset of around 1.6 meters. The main shock ran on the Paxton Ranch Fault Zone, right lateral, trending northwest, roughly 50 kilometers long. Field crews measured offsets along it that the California Geological Survey reports as reaching as high as 7 meters near the epicenter, though geodetic inversions, which model the slip at depth rather than measuring it at the surface, put the peak nearer 5 meters at 3 to 8 kilometers down. Either way, the desert floor moved by more than the height of a person, and in places by more than the height of a house. 2 fault systems at right angles, one triggering the other in 34 hours. A study in the journal Science described what had ruptured as an unmapped multi-scale network of interlaced orthogonal faults, meaning the crust there is not organized into the tidy long faults our maps show, but into a lattice of shorter cracks running in 2 directions at once, most of which nobody knew existed until they moved. The total mapped surface rupture from both earthquakes came to more than 68 kilometers. The field response logged over 6,000 individual site observations, of which more than 1,100 included actual measurements of ground offset. It remains one of the most completely documented surface ruptures ever recorded, and it did something else that is directly relevant to where we are standing now. The main shock rupture ran southeast and stopped just a few kilometers short of the Garlock Fault, a very large, very old structure that runs perpendicular to the San Andreas and had shown essentially no historical activity. It did not break the Garlock, but it triggered creep along 20 to 25 kilometers of it, about 4.5 kilometers south of the rupture. The Garlock, which had been considered locked and quiet, began to slide slowly at the surface because an earthquake nearby had changed the stress on it. That is the crucial concept for everything that follows. Earthquakes do not only break the rock they break, they redistribute stress across a very wide area, and rock that was already close to failing can be pushed over the edge by a change far smaller than you would expect. Which brings us north to Coso. The Coso volcanic field sits about 30 kilometers north of the magnitude 7.1 epicenter, or about 64 kilometers north of the town of Ridgecrest, depending on which reference point you measure from. Both numbers appear in the literature and both are correct. They are simply measuring to different things. The main shock rupture ran northwest. It was pointed, in other words, more or less straight at Coso. And about an hour after the main shock at 19 minutes past 9 in the evening on the 5th of July, a magnitude 5.4 struck 20 kilometers east-southeast of Little Lake, at the southern margin of the Coso volcanic field. That event was itself an aftershock of the 7.1, and it was the trigger for what happened next inside the volcanic field. The California Volcano Observatory published a statement the following day, the 6th of July, and the numbers in it are the ones I want you to hold up against this week. An average of about 30 earthquakes per hour have been detected since. 30 an hour, not 30 a day, 720 a day if the rate held. 4 days later, on the 10th of July, they published again with a firm account. The seismic activity at the southern margin of Coso, they wrote, was continuing at a rate of about 600 magnitude 1 or greater earthquakes per day. 600 a day. This week, Coso produced 208 catalogued events in 5 days. That is about 42 a day. 7 years ago, it was doing 600 a day, sustained, for the better part of a week. There is a number in that same statement which puts a very sharp edge on the comparison, and it concerns the largest events. Of the approximately 1,600 earthquakes detected at magnitude 1.0 or above since the 8th of July, they wrote, only 12 have been magnitude 3.0 or above, with the largest 2 registering 4.1, 12 above magnitude 3, in an episode running at 600 events a day. Largest 2, 4.1. This week's swarm produced 4 above magnitude 3, and its largest was 3.96. So on rate, this week is running at about 1/15 of the 2019 episode. On peak magnitude, this week is very slightly smaller than the largest events of 2019. On duration, 2019 went on for weeks, and this has so far gone on for 5 days. If you want to know whether Coso is escalating towards something over the past 7 years, that is your answer, and the answer is no. It is doing a considerably smaller version of a thing it already did, and the last time it did the bigger version, nothing happened. Which is exactly what the observatory said at the time, twice, in the same sentence both times. No ground deformation indicative of volcanic activity has been detected, and there is no imminent threat of an eruption. That should settle it, and for about a year it did settle it, until a group of scientists went back through the data, found something genuinely strange about how Coso responded to Ridgecrest, and published a result that made the front of one of the biggest journals in the world. And then, almost immediately, somebody at the survey published a paper arguing the whole thing was an artifact of the instruments. Part 9. The aftershocks that weren't there. Here is the thing about the 2019 Ridgecrest earthquake that took 2 years to notice. When a magnitude 7.1 ruptures, it changes the stress on every fault for a very long way around. Some faults get squeezed harder, which makes them less likely to slip. Others get unclamped, which makes them more likely to slip. This is not guesswork, it is calculable, and it has been calculable since the 1990s. You model the rupture, you compute how the stress field changed, and you produce a map of where aftershocks ought to appear. Do that for Ridgecrest, and the Coso geothermal field lights up. It sits north of the rupture, in an orientation where the co-seismic stress change should have promoted failure. The model says there should be aftershocks here. In June of 2021, a team led by Kyung-jae Im, with Jean-Philippe Avouac, Elias Hymeson, and Derek Ellsworth, published a paper in Nature reporting what they found when they looked. Their sentence is the whole paper in one line. In an area where changes in co-seismic stress should have triggered aftershocks. However, no aftershocks were observed there. Nothing. A hole in the aftershock map shaped like the geothermal field. Their explanation is the reason the paper made Nature, and it is genuinely remarkable. 30 years of geothermal heat production at Coso, they argued, had depleted the shear stresses within the geothermal reservoir, pulled heat out of rock and the rock contracts, contracting rock cracks, and that cracking, this is their wording, thermal contraction of the reservoir initially induced substantial seismicity, as observed in the Coso geothermal reservoir. But over 3 decades of doing that, the reservoir gradually ran out of stored elastic stress to release. By 2019, when Ridgecrest handed it a fresh stress increment, there was nothing left in the tank for that increment to trigger. The reservoir had been, in their term, de-stressed. Then they added a line that got a great deal of attention and deserved it. Such a distressed zone could, in principle, impede the propagation of a large earthquake. Read that slowly. A peer-reviewed paper in Nature suggesting that a geothermal power plant might function as a partial firebreak for earthquake ruptures, that by systematically bleeding stress out of a volume of crust, industrial heat extraction could make that volume harder for a large rupture to pass through. Caltech's own write-up of the work carried the headline that producing clean energy can diminish earthquake risk. It is an extraordinary claim, and it is an extraordinary claim about the exact patch of ground that produced 208 earthquakes this week. But it has a problem, and the problem had already been published a year earlier by somebody at the survey in a journal with rather less glamour. In June of 2020, J. Olcavan of the United States Geological Survey's Earthquake Science Center published a paper in the Bulletin of the Seismological Society of America titled, plainly, Seismicity Rate Change at the Coso Geothermal Field following the July 2019 Ridgecrest magnitude 7.1 earthquake. Cavan had noticed the same absence, and had also noticed that previous regional earthquakes had produced the same odd result, seemingly increasing seismicity all around Coso, while leaving the field itself untouched. So he checked it against a different catalogue, not the regional network, the local one, the Navy's. His finding, verbatim, I carry out seismicity rate change calculations using a catalogue of seismicity compiled using a local seismic network, and find that the Coso geothermal field behaves identical to the surrounding area. Identical, not suppressed, not de-stressed. The aftershocks were there the entire time, they were simply too small and in the wrong place for the regional network to record. And Cavan's explanation for why the regional network misses them is the fact we established several parts ago coming back to do serious damage. The differences, he wrote, are likely related to incomplete sampling of seismicity using the regional network due to the existence of a very shallow brittle ductile transition centered on the Coso geothermal field. The Coso field thus is prone to triggering from both teleseismic and regional earthquakes. There it is. The brittle ductile boundary at Coso is bowed up to 4 or 5 kilometres instead of the usual 11. That compresses all the seismicity into a thin, shallow layer, makes the events smaller on average, and pushes a large fraction of them below the detection threshold of instruments sitting tens of kilometres away. The regional network is not seeing a quiet volcano. It is seeing a loud volcano through a wall. 2 papers, both peer-reviewed, both recent, neither retracted. One says the earthquakes were not there, the other says the earthquakes were there and the network could not see them. I am not going to tell you which one is right, because I do not know, and neither does anybody else with certainty. Both mechanisms are physically real. Thermal contraction genuinely does induce seismicity, and IMS Group demonstrated that with data. Regional networks genuinely do undersample shallow small events, and Caven demonstrated that with data too. It is entirely possible both are partly true, that production has meaningfully distressed the reservoir, and that the regional catalogue understates what remains. But look at what this fight does to our number. 208 events. That figure came from the regional catalogue. The same regional catalogue that a USGS scientist has published a peer-reviewed paper about, specifically to argue that it systematically undercounts earthquakes at this exact location, for a structural reason that has not changed since 2020. 208 is not a measurement of the Coso swarm, it is a flaw. And this is where the whole story turns, because it means the reassurance and the uncertainty come from the same place. We are confident this swarm is not magmatic because the earthquakes are shallow, static, and above the melt, and because there is no deformation. But the network that counts the earthquakes is known to undercount them here. The network that measures deformation is 3 receivers, and the network that would smell the gas does not exist. Everything we know, says hot water. The problem is how little we know. There is one more finding from the Ridgecrest aftermath that belongs here, and it is the most direct evidence we have of what a magnitude 7 does to Coso's actual magma, as opposed to its faults. In 2024, a group led by Fei Chen modelled 4 years of post-earthquake deformation around the Ridgecrest rupture using both satellite radar and ground-based satellite positioning. Ground keeps moving for years after a big earthquake, partly because the fault continues slipping slowly at depth, and partly because the hot, weak lower crust flows in response to the stress change like cold treacle finding its level. To fit the data, they found they needed something specific: laterally variable low-viscosity zones beneath the Coso volcanic field. In other words, the crust under Coso is unusually soft, because it is unusually hot, and that softness shows up in how the whole region relaxed after the earthquake. They went further and suggested it may have shaped the earthquake itself, that those soft materials may reduce the width of the brittle part of the fault and thereby affect the northwestward propagation of the Ridgecrest rupture. Coso may be part of the reason the 7.1 stopped where it stopped. And then the line that matters most for tonight. Post-seismic viscoelastic relaxation of the event, they wrote, will cause contractional strain in the upper crustal magma reservoirs, which may counteract the extensional strain caused by the cosismic rupture. Contractional strain in the magma reservoirs. For 7 years, the aftermath of Ridgecrest has been gently squeezing Coso's magma bodies, rather than unclamping them. Whatever the 7.1 did to this volcano, the long-term effect on the melt has been compression, not release. So the Ridgecrest explanation for this week's swarm, that the big one woke something up and it has been building ever since, fails on 3 separate counts. The rate is 15 times lower than it was in 2019. The largest event is smaller than 2019's largest, and the measured post-seismic effect on the magma has been to squeeze it. Ridgecrest is not the answer, which leaves 2 candidates, and the next one has been sitting in plain sight for the entire video, a piece of industrial machinery drilled directly into the roof of the volcano that has been pulling superheated water out of this rock every single day since 1987. Part 10. The Plant on the Roof. If you drive north out of Ridgecrest on Highway 395 and look east across the desert, you will see steam. Not fumaroles, or not only fumaroles, cooling towers, pipe runs. The Coso geothermal field is one of the largest geothermal power operations in North America, and it is built directly on top of a volcano with confirmed magma beneath it, which is not a coincidence. It is the entire point. You put a geothermal plant where the rock is hot, and the rock is hot here because there is melt underneath. The scale of it surprises people who have never seen the numbers. The facility went online in May of 1987, after more than a decade of exploration and drilling. It consists of 4 power blocks, Navy 1, Navy 2, and 2 plants named for the Bureau of Land Management East and West. Between them they house 9 turbine generator sets, each rated at 30 megawatts, for a total rated capacity of 270 megawatts. Navy 1 and Navy 2 carry 3 units apiece. BLM East has 2, BLM West has 1. The last of the 9 came online in January of 1990. Navy 1 puts its power onto the grid at 115,000 volts, the others at 230,000. 270 megawatts is not a small power station. When it was running at full capacity, the survey described its output as sufficient to supply the needs of 270,000 homes. Underneath, the machine is bigger than the buildings suggest. Steam and brine are drawn from a well gathering system connecting more than 140 production and injection wells spread across almost 15,000 acres. The operator currently lists 99 production wells and 35 injection wells. Above ground, there are 140 miles of pipe, 12 inches in diameter and larger. The cooling towers move 50,000 gallons a minute, each. The turbines spin at 3,600 revolutions per minute. Roughly 80 people work on site. The fluid itself is the part that matters for our purposes. It comes out of the ground between 200 and 328 degrees Celsius. The operator quotes a consistent source temperature of 600 degrees Fahrenheit, which is close to 3 times the boiling point of water at sea level, and it stays liquid purely because of the pressure it is under. Wellhead pressures run from 85 to 500 pounds per square inch. Mass flow through the system exceeds 14 million pounds an hour. The brine carries between 7 and 18,000 parts per million of dissolved solids, mostly chloride, and its dissolved gas is 6% of the fluid fraction, of which 98% is carbon dioxide. Every one of those numbers describes an enormous, sustained, deliberate disturbance of the exact volume of rock where this week's earthquakes are happening. And here is the detail that made me stop when I found it. Coso's production wells run from 2,500 feet deep to over 13,000 feet deep. Convert that, roughly 0.75 kilometres to about 4 kilometres. The entire earthquake swarm, every catalogued event from the shallowest at 2.26 kilometres to the deepest at 3.51, falls inside that interval, not near it, inside it. The rock that is breaking is the rock the wells are in. That is not by itself proof of anything. Correlation of depth is exactly what you would expect regardless of cause, because the wells were drilled into the permeable zone, and the permeable zone is where the natural hydrothermal circulation happens too. The plant is there because the fluid is there. Earthquakes in a fluid-saturated fracture zone will occur at the same depth as the wells, whether or not the wells have anything to do with them. Any competent seismologist would say exactly that, and they would be right. But it does mean the question has to be asked properly rather than waved away, because there is a real mechanism published in a real journal, and it is operating right here. Before that, the second number worth knowing about this plant, because it changes how you think about what has been happening in that rock for the last 4 decades. The Coso field does not make 270 megawatts anymore. It has not for a very long time. In 2010, the average net capacity was about 180 megawatts. In 2011, it was 170. Those figures come from Fitch Ratings, which in May of 2012 downgraded $629 million of Coso geothermal power holdings pass-through certificates from a B rating to a CCC. The rationale is worth reading in the agency's own words, because credit analysts do not do drama. Geothermal resource depletion, they wrote. Coso's average net capacity declined over 5% to 170 megawatts in 2011, from approximately 180 in 2010. They projected that the debt service reserve would be fully depleted by 2017, leading to default. Today, the operator states that the facility produces about 145 net megawatts to Southern California Edison. Trace that line. 270 megawatts rated, with a peak net running capacity that reportedly touched 302, 180 by 2010, 170 by 2011. About 145 now. The field makes roughly half what it was built to make. That decline is the outward sign of something happening underground, and understanding what it is turns out to be the key to the entire induced earthquake question. The history of how this got built is worth a minute, because it explains why the instrumentation situation is the way it is. In the 1960s, a scientist named Carl Austin advised the Navy that there was a geothermal resource under China Lake worth developing. Through the 1970s, a team of government and university scientists ran field studies and concluded there was a potential resource of several hundred megawatts. One assessment put it at 650 megawatts electric with a nominal lifespan of 30 years. The first well went down in 1981. The turbines were built by Mitsubishi and Fuji and installed between 1987 and 1989. That sequence matters because it means the Navy has been the primary scientific presence at Coso since before the California Volcano Observatory existed. The observatory was only formed in 2012, replacing the older Long Valley Observatory that had been set up in 1982 to watch the caldera to the north. By the time a dedicated volcano observatory for the state came into being, Coso had already been an operating power station for 25 years, monitored by an organization whose interest was steam. The reservoir underneath is roughly 30 to 35 cubic kilometres of rock, depending on whose estimate you use, and the way the field is worked is a closed loop with a leak in it. Between 80 and 90 production wells run at any given time, drawing brine up under pressure. That brine flashes to steam twice, the double flash configuration, driving the turbines, and what is left is pumped back down through 30 to 40 injection wells. In 2009, under new ownership, a pipeline was built specifically to increase recharge to the reservoir, which tells you how seriously the depletion was being taken by then. There is a discrepancy in the public record about the output that I want to flag rather than smooth over. The survey's main page for the Coso volcanic field says the field supplies the needs of 270,000 homes. A California Volcano Observatory article published in September of last year says 4 interconnected power plants produce enough power to supply over 100,000 homes. Both are the survey. The lower figure is far more recent, and it lines up with what the operator says about current output, which suggests the higher number has simply been left standing on a page nobody has updated. Part 11. What 4 decades of cooling does to rock. A geothermal plant is not a mine. Nothing is removed permanently in the way or is removed. The brine that comes up the production wells is stripped of its heat and then pumped back down the injection wells, and in principle the system recycles. What does not come back is the heat. That is the whole business model. You're not selling water, you're selling the temperature difference between 280 degrees Celsius in the air, and every kilowatt hour that leaves Coso on a transmission line is heat that has been permanently taken out of a body of rock underground. Do that for 39 years, and the rock gets colder. Not uniformly, and not everywhere. The cooling front spreads outward from the wells through the fracture network, following the paths where fluid actually moves. But over decades, a substantial volume of the reservoir loses temperature, and rock, like almost everything else, contracts when it cools. The numbers here are small in percentage terms and enormous in absolute terms, because the volume is enormous. Granite has a thermal expansion coefficient somewhere in the region of 8 parts per million per degree Celsius. Drop the temperature of a cubic kilometre of it by 50 degrees, and you have removed something on the order of a millionth of its volume per degree, which sounds trivial until you remember that rock does not shrink gracefully. Rock is stiff and brittle. When a volume of it tries to contract while being held on all sides by rock that is not contracting, it cannot simply pull inward. It has to pull apart internally. It cracks. Those cracks are earthquakes. Small ones, mostly, the sort that need a downhole sensor to detect, but earthquakes nonetheless, and they are a direct, mechanical, unavoidable consequence of taking heat out of rock. This is not a fringe hypothesis. It is stated as established in the same Nature paper we looked at earlier, and I want to give the sentence again with the emphasis in the right place. Thermal contraction of the reservoir initially induced substantial seismicity, as observed in the Coso geothermal reservoir. Induced substantial seismicity, as observed, at Coso, in Nature. So the answer to the question everyone wants to ask, can a geothermal plant cause earthquakes, is not maybe, and it is not a nervous no. It is yes, demonstrably, at this specific location, published in one of the 2 most prestigious general science journals on Earth. Anybody who tells you geothermal energy cannot produce seismicity is either uninformed or selling something. There is more to it than thermal contraction too. Injection wells put pressurized fluid into rock, and pressurized fluid does exactly what we established in the third part of this video. It reduces the effective normal stress on faults and unsticks them. That is the mechanism behind essentially every well-documented case of induced seismicity anywhere in the world, from wastewater disposal in Oklahoma to enhanced geothermal projects in Europe. And Coso has been a deliberate testbed for this kind of thing. In 2002, the Department of Energy awarded $4.5 million over 5 years inside a $12 million program with the Energy and Geoscience Institute at the University of Utah, specifically to demonstrate hydraulic fracturing technology at Coso. The West Flank area adjacent to the field was was later a first-phase candidate for the Department of Energy's Enhanced Geothermal Research Program, with a test well drilled in 2009 to 9,480 feet, bottoming out at 580 degrees Fahrenheit. Fracturing was studied here on purpose, with federal money, to see whether you could crack the rock enough to improve production. So we have a volcano with a magma body under it, an industrial operation that has been cooling and pressurizing the rock above that magma body for 39 years. Federal experiments in deliberately fracturing that rock, a published finding that the operation has induced substantial seismicity and a swarm of 208 earthquakes occurring inside precisely the depth interval where the wells sit. Laid out like that, it sounds damning. So let me now do the harder and more useful thing, which is to explain carefully why it probably still is not the whole answer, and where the honest limits of the argument are. The first limit is the direction of the Nature paper's actual finding. Im and colleagues did not set out to show that Coso's plant makes earthquakes. They set out to explain why Coso did not make earthquakes when Ridgecrest should have made it. Their central claim is distressing, that production has, on net, drained the reservoir of stored elastic energy and made it less capable of producing triggered seismicity, not more. The line about substantial induced seismicity refers to the early phase of production, decades ago, when the cooling front was fresh and advancing rapidly. A reservoir 39 years into its life, producing half the power it once did, has already done most of its thermal contracting. The rock that was going to crack from cooling has largely cracked. The second limit is that we have no operational data. Nobody outside the operator knows whether anything changed at Coso in the week of the 20th of August. Whether a well was shut in, whether injection was rerouted, whether a new well came online or an old one was worked over. Those records exist and they are not public, and without them, saying the plant caused this specific swarm is not a scientific claim. It is a guess with a plausible mechanism attached. The third limit, and the one that answers the question people are actually worried about, is that induced seismicity does not erupt volcanoes. This deserves a proper explanation rather than an assurance, because the intuition behind the fear is not stupid. If you are cracking rock above a magma chamber, surely at some point you crack through. The answer is no, and the reason is the boundary we keep coming back to. Everything the plant does happens in brittle rock. Pressurized fluid opens cracks, thermal contraction opens cracks, and both effects propagate through a connected network of fractures. That network exists only where rock breaks rather than flows, which at Coso means from the surface down to about 4 or 5 kilometres, where the brittle ductile transition sits, bowed upward by the heat from below. Below that boundary, the rock does not have cracks in the relevant sense. It deforms by flowing, slowly, under sustained stress. A pressure change in a fracture network above it does not transmit across, because there is no fracture network on the other side to transmit into. It is like trying to push a wave of air pressure through a wall of tar. And the magma sits below that boundary. Every estimate we have, 5 kilometres at the most optimistic, 10 to 20 at the more typical, puts the melt on the far side of a layer of rock that physically cannot carry the kind of stress change a well produces. The plant is working on the roof, the magma is in the basement. The floor between them is not made of anything that conducts what the plant is doing. There is also a simple empirical check, and it comes from the operators themselves, published in the technical literature. After several decades of geothermal production and seismic monitoring, there have been no adverse effects experienced in geothermal operations or locally due to seismicity. 39 years, thousands upon thousands of induced events down to magnitude minus 0.5, and the field has never produced anything that damaged the plant that caused it. Part 12. So, did we do this? Let me give the straight answer, because I think people are owed one, and because dancing around it is how trust gets lost. Is the Coso geothermal operation contributing to this swarm? Almost certainly yes, at least in part. The plant has been altering the pressure and temperature of this exact volume of rock every day for 39 years. It is not physically possible for that to have no effect on when and where small faults in that volume slip. The swarm is in the well interval. The mechanism is published. The honest position is that the plant is part of the system now. It is not an observer of this rock. It is a participant in it. Is the geothermal operation going to cause an eruption at Coso? No. And that is not a hopeful no. It is a structural one. The operation acts in brittle rock above a boundary that does not transmit its influence downward, and the melt is below that boundary. There is no pathway. Is the swarm therefore man-made rather than natural? That framing is the one I would push back on hardest, because it assumes those are two separate categories, and at Coso they stopped being separate categories in 1987. Coso was one of the most seismically active places in the United States before anybody drilled a well there. The field produces dozens of magnitude 1 and 2 events in an ordinary week. It produced a swarm of more than 300 earthquakes in February of 1992, 8 of them above magnitude 3, the largest a magnitude 4 at 19 minutes past 3 in the morning on the 19th of February, in a pattern 3 kilometres long, elongated north-northwest at 3 to 5 kilometres depth, which, if you're keeping track, is almost exactly the geometry of this week. It produced a swarm in 1982 with thousands of events, the largest a 4.9. In 1996 and 1998 it produced magnitude 5.3, 5.1, 5.2 and 5.0 events within a day of each other. In 2009, over a single week, 429 earthquakes, including a 5.2, a 4.9 and a 4.7 inside 1 hour. Coso does this. It has always done this. This week's swarm, with its largest event at 3.96, does not crack the top 10 in the field's own recorded history. What the plant has done is superimpose a continuous industrial signal on top of a natural process that was already extremely noisy, in a way that after 4 decades cannot be cleanly separated. When rock at Coso breaks, some of the stress that broke it came from the Pacific Plate grinding past North America. Some came from hot water circulating as it has for hundreds of thousands of years, and some came from a turbine hall taking heat out of the ground. There is no meaningful way to assign percentages, and anyone who offers you percentages is guessing. There is one more piece of evidence about how close to failure this crust sits, and it is the single most astonishing statistic I found while putting this together. In 2020, a team led by R. Alfaro Diaz examined 13 years of seismic data from Coso, from 2004 through 2016, using the USARA Transportable Array and the Southern California Seismic Network. They looked at every earthquake of magnitude 7 or greater anywhere on the planet during those 13 years, 211 of them, and asked a simple question. When the surface waves from that distant earthquake swept across Coso, did Coso respond? 41 of them did it, 19%. 32 produced a statistically significant increase in seismicity in the seconds and minutes after the waves arrived. Of the 41, 28 were instantaneous and 13 were delayed. Roughly 1 in 5 great earthquakes anywhere on Earth makes Coso shake. Not a big earthquake nearby. A magnitude 7 in Chile, in Japan, in Indonesia, 10 or 15,000 kilometers away, whose surface waves arrive at Coso having crossed the entire planet, and are by then a slow, gentle rolling of the ground measured in fractions of a millimetre. And 1 time in 5, that is enough to break rock at Coso. The authors suggest Coso may be optimally oriented for triggering from West Pacific and South American sources, because the transient stresses arriving from those directions happen to align favourably with the local stress field. They found no correlation with the distant earthquake's depth, its peak dynamic stress, or its focal mechanism. Think about what a crust has to be like for that to be true. It has to be hot, thoroughly fractured, saturated with pressurized fluid, and loaded so close to its failure threshold across such a large volume that a passing wave from the other side of the world is enough to tip parts of it over. That is Coso in one statistic. Not a volcano straining to erupt. A volcano whose upper crust is permanently delicately on the edge, where a small nudge from almost anywhere produces a large number of small earthquakes, and where 208 events in 5 days is what a nudge looks like. The remaining question is what nudged it this time, and the honest answer is that we do not know and probably never will, because the 3 candidates, regional stress, hydrothermal circulation, and the plant, all operate on the same rock at the same depth through the same fracture network. What we can say is which candidate is not on the list, and that brings me to the 3 explanations that are circulating hardest online, all of which have a real grain in them, and all of which fall apart when you push. There is a broader point buried in that history, and it is the reason this story is worth 2 hours rather than 2 minutes. We have spent a century building an intuition that natural hazards are things that happen to us. An earthquake arrives, A volcano erupts. Our role is to be somewhere else when it does. That intuition is increasingly wrong, and Coso is one of the clearest demonstrations of why. There is now no state of this rock that can be described as untouched. The stress field in the top 4 kilometres of the Coso volcanic field is the sum of plate tectonics, hydrothermal circulation, the aftermath of a magnitude 7.1 in 2019, the passing surface waves of every great earthquake on the planet, and 39 years of a power station taking heat out of it. Those inputs are not separable, and they will never be separable, because you cannot run the control experiment. There is no second Coso with no plant on it, which means that for this volcano, and for a growing number of places like it, the question of whether an event was natural or man-made has quietly stopped being answerable. Not because the science is weak, but because the categories stopped being distinct decades ago. The useful question is a different one, and it is the one the observatory actually asks. Not who or what caused this, but is anything about it heading toward the surface? That question has an answer, and the answer tonight is no. Part 13. The base, the number, and the craters that aren't. 3 claims are doing the rounds about this swarm, and I want to take all 3 seriously before I take them apart, because each one is built on something true, and dismissing them without engaging is how you lose people who are asking a reasonable question badly. The first is the magnitude. The claim is straightforward. The earthquake came in as a 4.1. Within hours it was a 3.9. Then it was a 4.0. Somebody is managing that number downward to keep people calm, and if they are managing that one, they are managing others. The grain of truth is that the revision is completely real. It happened in public, it is documented, and anybody watching the event page that night saw the number change under them. That is genuinely disorienting the first time you experience it, and it is fair to ask why. The debunk has 2 halves, and the first is simply the direction of travel. A cover-up revises down and stays down. This one went 4.1, then 3.9, and then back up to a value that rounds to 4.0. If the objective were to shrink the earthquake, the second revision makes no sense at all. The second half is more interesting, and it explains the whole thing. The number did not just change, the kind of number changed. The first estimates were local magnitude. The scale Charles Richter built in 1935 computed from how far the needle swings on a seismometer, corrected for distance. It is fast, it is automatic, and it can be produced within seconds of the waves arriving. It is also crude, because the size of the swing depends on which stations happen to report first, on the rock those stations sit on, and on the direction the rupture happened to be pointing. The final published value is a moment magnitude. That is a fundamentally different quantity. Moment magnitude is computed from the seismic moment of the rupture, the rigidity of the rock, multiplied by the area of the fault surface that slipped, multiplied by how far it slipped. It is a measurement of the physical size of the break, and producing it requires modelling the waveforms properly, which requires an analyst and time. The catalogue entry for this event says 40 stations, azimuthal gap 35 degrees, magnitude type moment magnitude, status reviewed. Somebody sat down and did the work, and the answer they got was 3.96. Expecting a local magnitude and a moment magnitude to agree is like expecting a car's speedometer and its odometer to give you the same number. They measure different things, and the full revision history, every value, every timestamp, every contributing agency, is left permanently attached to the public record, which is a very strange way to hide something. There is a final point that I find genuinely decisive. The dense seismic network at Coso is not operated by the survey. It is operated by the United States Navy, and it resolves earthquakes down to magnitude minus 0.5. If anybody wanted to control the earthquake count at Coso, the public catalogue is not where they would need to do it, and the agency being accused is not the one holding the detailed data. The second claim is the base. Most of the Coso volcanic field sits inside the Naval Air Weapons Station at China Lake. The swarm is at 2.5 kilometres depth. The Navy runs the local network. The Navy's Geothermal Program Office holds jurisdiction over geothermal development on all military-owned land in the country, with a standing policy that no development proceeds if it would adversely affect the military mission. So, something is being done down there, and we are not being told. The grain here is real, and I am not going to pretend otherwise. This is a restricted military installation. There is a genuine information asymmetry. The detailed seismic catalogue does belong to the Navy, and the operational data from the plant is not public. If you feel there are things about this location you are not being shown, you are correct, and that instinct is not paranoid. But the specific claim that these earthquakes are explosions of some kind fails on physics, and it fails immediately and unambiguously. An explosion and an earthquake are different kinds of source, and they radiate differently in a way that is obvious on a seismogram. An explosion is compressional. It pushes outward in every direction at once, so the first motion recorded at every station on Earth is the same, up. It produces an enormous P wave relative to its S wave, because a symmetric outward push generates very little shear. Its energy is concentrated at high frequency in a short, sharp, simple pulse. An earthquake is a shear source. Two blocks slide past each other, which means the ground is pushed in some directions and pulled in others, in a four-lobed pattern. Stations in one quadrant record a first motion that is up, stations in the next record down, and the alternating pattern is what lets seismologists determine the fault orientation. Earthquakes generate a strong S wave, often far stronger than the P. This distinction is not a subtlety. It is the entire technical foundation of nuclear test monitoring under the Comprehensive Nuclear Test Ban Treaty. Global networks have been discriminating explosions from earthquakes on exactly this basis since the 1960s, and they do it reliably at magnitudes far smaller than 4. And then there is the shape of the sequence itself, 208 events over 5 days, hundreds of them below magnitude 2, 16 on the first day, 52, then 9, then 116, with the largest arriving on day 4 at 1 in the morning. That is not a test schedule. Nobody schedules 116 detonations in a day and then stops for a day and starts again. That is a fracture network relaxing. Finally, the stations that recorded this are not on the base. The Southern California Seismic Network is operated jointly by Caltech and the survey. Its instruments are distributed across the whole of Southern California, and its data streams are public in near real time. That is how I have the numbers I have been giving you all video. Nobody had to be let through a gate. The third claim is the strangest and the easiest, and it is about the domes themselves. Look at aerial imagery of the Coso field, and you will see circular structures with raised rims and sunken centres scattered across the desert floor, and you will find people online who are certain those are impact craters, that this is a strewn field, that something came down here, and that the volcano story is a cover. I understand why the images produce that reaction. They genuinely do look like it, and a raised rim around a depression is a shape our brains file under impact. But the rock settles it in about 10 seconds. These are extrusive rhyolite domes. Rhyolite is magma with about 77% silica, and at Coso the silica content of the volcanic glass is essentially constant at that figure across the whole field, which is itself a chemical fingerprint no impact could produce. Silica that concentrated makes magma so viscous it barely flows. When it reaches the surface, it cannot spread. It piles up directly over its own vent, cools from the outside in, and then sags slightly at the centre as the trapped gas escapes and the interior contracts. Raised rim, sunken middle, exactly what you see. Then there is the obsidian, which is the part I find genuinely lovely. Obsidian is volcanic glass, rhyolite that cooled so fast the atoms never organised into crystals. It forms from silicate melt and from nothing else in nature. Coso is full of it, and it was so good that people came a very long way for it. Between roughly 3,000 and 1,000 years ago, native peoples worked these hillsides systematically, cutting benches into the slopes and digging pits to reach fresh material. Coso obsidian has been identified in archaeological sites at San Diego, in San Luis Obispo County, at Santa Barbara, and across the Mojave. Geochemists can distinguish at least 4 separate subsources within the field: Sugarloaf, West Sugarloaf, Joshua Ridge, and West Cactus Peak, because each dome erupted magma with a slightly different trace element signature, and those signatures sort into 7 distinct age and chemistry groups. An impact does not produce obsidian with a constant silica content that separates into 7 chemically distinct eruptive episodes spread over 1 million years. A volcano does exactly that. The domes are volcanic, the field is volcanic, and the reason it looks so strange from the air is that this specific kind of eruption produces a landform most people have never been taught to recognize. So all 3 claims have a real seed, and none of them survives contact with the data. The magnitude revision is a scale change published in the open. The military angle names a real information asymmetry, and then attributes it to a source type that the seismograms rule out. The impact crater claim mistakes an unfamiliar volcanic landform for a familiar one. And notice that none of them is the interesting question. The interesting question is not whether somebody is lying to us about Coso. It is how much anybody actually knows, which is a completely different problem and a much less comfortable one because it does not have a villain in it. Part 14. The Ones We Watch Instead. While Coso was producing 116 earthquakes in a day with no official comment, the volcano that everybody actually watches was doing something with its ground that Coso is not doing, and the contrast is the cleanest way I know to show you what a real precursor looks like. Kilauea, on the island of Hawaii, has spent this year in an episodic fountaining eruption, and the pattern is so regular that the observatory has been publishing forecast windows for individual episodes. Episode 53 began at around 3:45 in the afternoon, local time on the 12th of August, and ended abruptly at 23 minutes past 1 the following morning. Then the pause began, and the forecasting resumed. The forecast is not built on earthquakes, it is built on the shape of the ground. Between episodes, Kilauea's summit inflates as magma refills the shallow reservoir, and the tilt meters and satellite positioning stations record the swelling in real time. Then, in the final day or two before an episode, something counterintuitive happens. The summit deflates slightly, and then rises sharply just before the fountains start. The observatory watches that curve, fits it, and publishes a window. As of the 21st of August, the window read the 22nd through the 27th. 2 days later, with more data, it had been revised to the 24th through the 28th. That is what it looks like when deformation data is actually telling you something. Not a vague sense of unease, a date range, published in advance, revised as the curve updates, on a volcano where the instruments are dense enough to resolve the shape of the ground hour by hour. Now hold that against Coso, where the deformation network is 3 receivers, 2 of them 20 years old or older, and where the multi-decade trend is subsidence. The question is not whether Coso's flatline is reassuring. It is. The question is how much a flatline is worth when it is drawn by 3 instruments. 200 kilometres north of Coso, the same lesson arrives from the opposite direction. Long Valley Caldera is California's very high-threat volcano, the one that produced the Bishop Tuff, the one with 46 GPS receivers and 9 tilt meters, and a research program that has been running since the Long Valley Observatory was established in 1982. It has had 4 documented episodes of unrest in living memory: 1978 to 83, 90 to 95, 96 and 97 to 98, with earthquake swarms and ground rising by almost half an inch a year. In October of 2023, a Caltech group led by Ettore Biondi published a study that used something new. Instead of seismometers, they used a 100-kilometre stretch of fibre optic cable, reading the tiny stretches and compressions in the glass caused by passing seismic waves, a technique called distributed acoustic sensing, which turns one cable into the equivalent of about 10,000 single-component seismometers. Over 18 months, they recorded more than 2,000 seismic events, most far too small to feel, and processed them with a machine learning algorithm to build an image of the crust down to 10 kilometres. What they found was a lid. The magma chamber, at around 12 kilometres, is capped by hardened, crystallised rock, magma that has cooled and solidified into a solid roof. Zhongwen Zhan, who leads the lab, put it plainly. We don't think the region is gearing up for another supervolcanic eruption, but the cooling process may release enough gas and liquid to cause earthquakes and small eruptions. Long Valley is not loading, it is cooling and settling, and the earthquakes it produces are the sound of that process rather than the sound of a system building toward something. The geodesy agrees. In January of this year, the observatory reported that the central part of the caldera has subsided by about 6 centimetres since 2021, the most significant subsidence at Long Valley since detailed measurements began in the 1980s, after decades of inflation that had accumulated nearly a metre of uplift. The GPS station in the middle of the caldera peaked at 22 centimetres of uplift in 2022 and has been coming down since, reaching 15 by 2025. So California's most dangerous volcano is deflating, and its magma chamber has a solid roof on it, and we know both of those things in that much detail because there are 46 receivers on it. The rest of the planet on the day Coso peaked was ordinary. A magnitude 6.0 struck at 43 kilometres depth, about 33 kilometres south-southwest of Honshu, in northern Japan, in the middle of the afternoon Coordinated Universal Time on the 23rd. It followed a magnitude 5.8 the previous day at 61 kilometres depth near Toride, much further south. The two of them bracket the Japan Trench, north and south, which is a normal week for a subduction zone that produces this kind of thing constantly. Yellowstone, which is the volcano that occupies more public anxiety than every other American volcano combined, showed essentially nothing on its seismograms all day. There was a magnitude 1.1 near Chester, New Jersey, which is notable only because New Jersey. The loudest volcanic ground in the United States on the 23rd of August 2026 was not Yellowstone and was not Long Valley. It was an unnamed scatter of lava domes on a Navy base in the Mojave Desert that most Americans have never heard of, and no agency said a word about it. There is a line from the California Volcano Observatory that I think about a lot, and it belongs here. Volcanic eruptions occur in the state about as frequently as magnitude 6 or larger earthquakes on the San Andreas Fault. At least 10 eruptions have taken place in the past 1,000 years, 10 eruptions in 1,000 years. The most recent was Lassen Peak, which erupted from 1914 to 1917, within the lifetime of people who were alive when some of us were children. California is not a place where volcanoes are a theoretical concern. It is a place with 16 threat-ranked young volcanoes, 8 volcanic areas under weekly surveillance, and confirmed molten rock beneath 7 of them. Coso is one of those 7. It is watched by 1 seismometer and 3 receivers, and this week it did something none of the other 6 did. It is worth putting a number on the gap between Long Valley and Coso because the words very high threat and moderate threat do not convey it. Long Valley's defining event was the Bishop Tuff eruption, 760,000 years ago. More than 100 cubic kilometres of material fell as ash. Roughly 200 more came out as pyroclastic flows that swept across more than 2,200 square kilometres of what is now eastern California. About 350 cubic kilometres ponded inside the caldera itself and welded into rock that is nearly 200 metres thick just south of the rim. The caldera it left behind is 16 by 32 kilometres, and within 100,000 years of the eruption the floor of it had domed back up by about 400 metres as the system recharged. Coso, across 6 million years of activity, has produced about 35 cubic kilometres in total, and 30 of that came out during one Pliocene interval between 4 and 2.5 million years ago. The 38 rhyolite domes that give the field its character, the ones that look like craters from the air, represent a few cubic kilometres between them. That is the difference between rank 18 and rank 72. It is not that Long Valley is watched because it is famous. It is watched because it has done something Coso has never come close to doing, and because there is a town on it. The odds published for Long Valley are instructive too. The survey puts the chance of an eruption somewhere along the Mono Inyo chain in any given year at roughly 1 in a few hundred, somewhat less than 1% annually, and the odds that such an eruption significantly affects any specified place along that chain at roughly 1 in 1,000 per year. 20 or so eruptions have occurred along it in the past 5,000 years, all but 3 of them explosive, and the survey's own summary is that scientists see no evidence that an eruption of catastrophic proportions might be brewing beneath Long Valley caldera. Those are the numbers for California's most dangerous volcano. Cosos are smaller in every dimension that matters. Part 15. What would actually change? The answer. So where does that leave us? The Coso volcanic field, quiet for 40,000 years, produced 208 catalogued earthquakes in 5 days, running at 8 times its own recent background rate. It doubled its entire annual count of magnitude 3 events in that window. Its largest earthquake, a moment magnitude 3.96, struck at 55 seconds past 12:59 in the morning on the 23rd of August at a depth of 2.83 kilometres, and it was followed 80 seconds later by a 3.36 and 77 minutes later by a 3.51. The sequence had no main shock, built in 2 pulses with a near-silent day between them, and came out of a lens of rock about a kilometre across and a few hundred metres thick. Every test we can apply says this is not magma. The earthquakes are not migrating upward, which is the single clearest precursor there is. They are all volcanotectonic, sharp, high-frequency, brittle, with no long-period events and no tremor reported, which is the signature that distinguishes rock breaking from fluid moving. They sit above every published estimate of the magma reservoir, separated from it by a boundary of rock too hot to crack. And the ground has been subsiding, not inflating. For the entire 3 decades we have been able to measure it. The probable answer is hot water, pressurized hydrothermal fluid moving through a fracture network at 2.5 kilometres, unsticking small faults as it goes, in pulses, which is why the sequence stopped and restarted rather than decaying. Superimposed on that, very likely, is the influence of 39 years of industrial heat extraction from the same rock, in a way nobody can cleanly separate and nobody outside the operator has the data to try. That is a good answer. I believe it. It is what I would bet on, and it is what the observatory has implicitly concluded by leaving the alert level where it is. But I want to be honest with you about what that confidence rests on, because this is the part that has stayed with me since I started pulling the numbers. The observatory's own published rule is that deformation is the discriminator. Magma has to displace rock, and displaced rock swells, and swelling is measurable. If you do not see deformation, the rule says, the source either is not magmatic or is too deep to matter. That rule is correct, and it is the right rule, and it is the reason we can be relaxed about Coso tonight. And the network that applies that rule at Coso is 3 GPS receivers. The newest was installed in 2006. There are no tilt meters. There are no strain meters. There is no gas monitoring at all. No instrument watching for the carbon dioxide that comes out of solution first, deepest, and earliest, before anything else in the system changes. Meanwhile, a peer-reviewed paper by a survey scientist argues that the regional seismic network systematically undercounts earthquakes at this exact location. For a structural reason, the brittle ductile boundary bowed up to 4 or 5 kilometres, that has not changed and will not change, which means 208 is not the number of earthquakes that happened at Coso this week. It is the number we could see. The reassurance and the uncertainty come from the same instruments. That is the whole of it. We're almost certainly right, and the margin between almost certainly and certainly is exactly the width of a monitoring network that was built in proportion to how much an eruption here would cost, rather than in proportion to how hard this particular volcano is to read. So here is what to watch, in order of how much it would actually mean. The first is the earthquakes moving, not more of them, shallower ones, or a new cluster appearing to the west, because the survey's hazard assessment states in plain terms that future eruptions are more likely in the western half of the Coso volcanic field. Migration is the signal, volume is not. The second is the character of the signals changing. If the sharp, knife-cut volcano-tectonic events start giving way to broad, wobbly, long-period ones, that is the transition Mount St. Helens made in 2004 before it began building a dome, and it is the single most meaningful thing a seismogram at a volcano can do. The third is any inflation at all on those 3 receivers. Any reversal of a 30-year subsidence trend, however small, would move this story from hydrothermal to magmatic in a single afternoon. The fourth is gas. New fumaroles, or a change in what the existing ones at Coso Hot Springs are exhaling. Nobody is measuring this, which is precisely why it would have to be noticed by a person on the ground rather than by an instrument. And the fifth is the observatory itself, not an alert change, an information statement. The observatory has said explicitly that an information statement is the first heads-up it gives before changing a volcano's alert level. It is a deliberately low bar. As of tonight, none has been issued for this swarm, and the most recent notice the observatory has ever published naming the Coso volcanic field is dated the 11th of July 2019. None of those 5 has happened. The alert level is normal. The color code is green. The correct answer to the question this video asked is, yes, it is moving again, and no, it is not what you are afraid of. But there is a version of that answer I cannot give you, and it is the version where I tell you we would definitely know. Because the truth is that at a volcano with confirmed magma underneath it, in a state that has had 10 eruptions in 1,000 years, the difference between a swarm that means nothing and a swarm that means everything is a measurement of how much the ground has swelled, and at Coso that measurement is made by 3 boxes bolted to the desert floor, the newest of which was installed the year the first iPhone was still a rumour, which leaves the one thing worth actually checking, and it is not the earthquake count. Over the next fortnight those 3 receivers will either keep drawing the line they have drawn for 30 years, sloping quietly downward as the reservoir gives up more of its heat, or they will do something they have never done. And if some of them happen to be offline, as Coso stations sometimes are, then for that stretch of time the answer will not be reassuring or alarming. It will simply not exist.